So we're continuing looking at the AP Calc testing tips and advice. This is the second page. So we start off here at the top of the page with chain rule. So chain rule, to remember, something to remember is that keeping in mind that these are composite functions. We have function within a function. Sometimes there are three functions, function within a function within a third function. So that is most common in trig functions. Sometimes you see this cosine cubed of 4x, and whenever we see this, it's best if we rewrite it using brackets so that we can visually see the bracket, the cosine, and the parentheses, and they create three different layers that we have to keep track of. So for this instance here, we can think of outside, inside, and innermost function. So the outside function is the bracket cubed, which we do power rule for. And then we move on to the cosine parentheses, which is negative sine of u. And then finally the 4x. So if we write it out this way, it's more clear, visually it's clearer as to what needs to happen in order for us to do the chain rule portions correctly. All right, so if a problem asks for you to find a horizontal tangent line, you want to locate the derivative equation, dy dx, and set the numerator equal to 0. Now, if the problem asks you to find the vertical tangent line, then you're going to locate the denominator of your derivative equation and set that portion equal to 0. So here's an instance of an example here. Let's say dy dx was 3x minus 6 over 4y plus 2. If I want to find where there's a horizontal tangent on the original graph, the original function, then I'm going to take the numerator portion of my dy dx and set equal to 0 and solve for x, and that will tell me the location of a horizontal tangent. And if I want to locate where there's a vertical tangent, basically where the slope is undefined slope, I'll put that here. Then we take the denominator of the derivative and we set that equal to 0, and that will locate, if there's a variable there, we can locate where that vertical tangent is. Okay. All right, 18th item here, local linearization or linear approximation. This is just a fancy way of saying create your tangent line equation and then plug in the decimal. So we know how to find the tangent line equation. Also went over that on the first page here. We find the ordered pair, we find the slope, and we put in the point slope form. Now, once we have it in this form, if we want to do a linear approximation, we just take whatever decimal is and just put it in for that x. Okay. So keep in mind the steps of linear approximation. It sounds complicated, but really you're just doing one additional step after you find your tangent line. After you find your tangent line, you just plug that decimal into that into the x of your linear equation. In FRQ sections, AP exams FRQs tend to insert concepts like IVT or a combination or mixture, or these just tend to show up a lot. So IVT, EVT, mean value theorem, roles, L'Hopital's rule, first theorem of calculus, second derivative test, related rates into parts of problems. So let me just go through each of these theorems here, these main theorems. IVT, there's no calculus involved here. This is more of a common sense thing that makes sense, that if a function is continuous, meaning that if there are no breaks in the graph, then that graph is going to reach all the y values between the endpoints at least once. So if we start off at a y value of -5 and we go all the way up to a y value of 6, then between the two endpoints, the graph has to cross every y value between -5 and 6. Right? That's just something that makes sense. So that's what intermediate value theorem tells us. Extreme value theorem says that if a function is continuous, we can find absolute max, absolute min by considering and testing just the endpoints and relative max and relative mins. Okay. All right. Mean value theorem and roles are very similar. They are kind of the same. Just Rolle's theorem is a more specific version of mean value theorem. So mean value theorem says if a function is continuous and differentiable, meaning it's a smooth curve, then we can guarantee a specific slope of the tangent line by finding the slope between the endpoints. So here's the formula. F of b minus f of a over b minus a will give us the slope between the endpoints. F prime of c will give us the slope. Means that we can locate that particular slope of the tangent line on the curve. So here's a visual drawn out example here. MVT guarantees a slope value on the curve. So whatever we find between the endpoints is the slope that we can guarantee. So let's say the slope here is 2, is a slope of 2, steepness of 2. Then because there's a steepness of 2 between endpoints A and B, then there must be at least one other steepness of exactly that value, of exactly 2. And we can see that I can draw a parallel line to indicate that, yes, I can find a point that is matching that slope of 2 or whatever this is between the endpoints. Okay, so that's what mean value theorem guarantees. Whatever slope we find between the endpoints, there must be that specific slope value at least once showing up between my left and right endpoints. Okay. Now Rolle's theorem is very similar. Rolle's theorem is also guaranteeing a slope, but it's a very specific slope. It has to be a slope of 0. So we can only guarantee a slope of 0 if points A and B are directly across from each other, right? That they are exactly at the same height. And in order for us to guarantee that same height, they have to share the same y value. Okay, so if f of a is equal to f of b, then we know that we're drawing a horizontal line between those endpoints, which means that there must be at least a slope of 0 somewhere between the endpoints. So Rolle's theorem guarantees a slope of 0 somewhere on the curve as long as my endpoints, well, first off, as long as the graph is continuous and differentiable, and as well as the endpoints being the same y value. There's also just some adapted versions of mean value theorem and Rolle's theorem. So mean value theorem says take f prime, set it equal to the slope between the endpoints, and if we solve for c, we can find that location where that specific slope is going to exist on the curve. We can also adapt this with one derivative down. So I can also do the slope between the endpoints of my derivative graph and use that to figure out that there must be at least a point on the G double prime graph that shares this exact value. Okay, and we can also adapt Rolle's theorem to the second derivative, right? Because this holds for from f of x to f prime, we can also start at the, or I use a different variable here, but we're starting at the derivative level, and we can guarantee f double prime or G double prime equals 0. Other common theorems that comes up is first fundamental theorem of calculus. I think we went over that on the previous previous page. Second theorem is just really taking advantage of the inverse procedure between derivative and integrals and how they kind of undo and cancel each other out. Now, second derivative test is not one that it sounds like one that is using the second derivative function to find whether a graph is concave up or concave down, but it actually does the same thing, has the same result as the first derivative test, and that is using the second derivative function to find a relative max or relative min. So we know what a first derivative function is. First derivative test is where we set f prime equal to 0, and then we use a sign line to determine whether that critical point is relative max, relative min. Now, the second derivative test also takes that critical point that we find from f prime, but rather than using a sign line, we're plugging this critical point into the second derivative function. And if the second derivative functions, if we plug into the second derivative function and then the evaluation gives us a positive number, we know it must be part of a relative minimum. If that evaluation of that critical point that we found from f prime inserted into the second derivative function gives us a negative value, then we know it must be a relative minimum. Okay, and just to kind of give a visual example of that, let's say a function is differentiable and we have order pair 3, 4, and f prime of 3 is equal to 0. So we have already guaranteed that there's a slope of 0 at 3, but rather than using a sine line, we're going. Let's say we plug that 3 into the second derivative function, and in return we get a positive 6. Now, positive 6 for a second derivative function represents that this point must be part of a concave up graph, right? Concave up corresponds with a second derivative value that's positive. So the function must be concave up. So imagine you're pairing these two properties together. You know it's part of a slope 0, but it's also shaped in the concave up way. So the only way that we can put those two properties together is if it looks like this, right? This is the only way that we can create a slope 0 and also part of a concave up graph. And because of these two properties existing on the same x value, we know that we can conclude that this point must be part of a relative minimum. We can conclude that this order pair 3, 4 must be a relative minimum. Now, likewise, let's say, again, we start off with the fact that our critical point is at 3. There's a slope of 0 at 3. But now, when we plug 3 into the second derivative function, we get back a negative number. So if we get a negative number in return, we know that the conclusion that we can make is that the function must be part of a concave down graph. And if it's part of a concave down graph, then we can conclude that, well, slope 0 and concave down, visually, that convinces us that must be a relative maximum. I think the confusion that comes with this particular second derivative test is that students want to associate positive number with relative max and a negative number with relative minimum just because it just makes sense. But I think if we verbalize this as concave up and we draw the picture, I think if we make those two steps, we can convince ourselves, okay, that's obviously not a relative max, that's a relative minimum. And then the third thing is, let's say f prime of 3 is equal to 0, and the second derivative value also gives us 0. This means that we have an inconclusive test. This is not a good test to determine whether there's a relative max or relative min. We will have to rely on a different test, such as the first derivative test, to conclude whether our order pair is a relative max or relative min or neither. Okay. I think I talked about relative related rates previously, but again, we involve time. If we see rate, if we see, for instance, find the rate in meters per second of a person walking, find the rate of change of surface area, find our balloon rising at 4 feet per second. Anytime that you see time involved, usually that's a good hint that most likely is going to be related rates. Just because our slope is 0, and even though critical points exist, that doesn't guarantee a relative max or relative min. So just because there's a slope of 0, we still have to do additional checks before we can conclude whether that's a relative max or relative min. Likewise, with the second derivative function, if we want to confirm that a point is a point of inflection, we can't just look at the second derivative and just because it's a critical point, that's not enough to conclude that it's a point of inflection. It's a potential point of inflection, but we have to push it through a sine line test. So example here for if we find f prime is equal to 0, let's say points A and B, we got to push it through the sine line and see if there's a change in signs to determine whether there's a relative max or relative min. Same thing here. Just because we find C and D, 2 points being places where my second derivative value is 0, it doesn't guarantee a point of inflection. It's a critical point, but a point of inflection can only occur if there's a change in sign. And if there's no change in sign, it only stays as a critical point, but it doesn't graduate to a point of inflection unless there's a change in sign. All right. A couple of more minor topics that could show up is if you're asked to find the derivative of a log or a natural log expression, such as one that looks like this, we don't want to find the derivative initially because it's just too complex. There's an easier way to go about it, and that is by expanding. So if you see a messy log expression, try to expand it first before you do anything with the derivative. So this is what that example looks like. So if we have a messy natural log expression, we can rewrite it first using radical form, or convert radical to rational form. And then we have natural log of a times b over c. We can expand that out into natural log of a plus natural log of b minus natural log of c. And then along the way, after we do that, we can also bring the exponents down in front. And then once we have everything expanded out, then we can apply u prime over u for each of the derivatives, for each of the terms to get to the derivative function. Okay. Now this is the next example here. If a problem involves exponential function of a variable raised to another variable, let's say I have a x raised to an expression that also has a variable, then we don't have a rule that can handle this derivative. The only way to go about doing this is by making progress is to go through log differentiation. So the steps that we take for log differentiation is where we introduce natural logs to both sides of the equation that will force this exponent to be able to be brought down, and then we can move, have a much easier path to our answer once we don't have a ugly exponent value with a variable in it. So let's go through the steps here. If I have x raised to the power of 1 minus x squared, I can take the natural log of both sides. I can bring that exponent down in front. And once I have everything expanded out, then I see that, well, to get from here to the derivative, I have y involved. I got to go through implicit differentiation. So natural log of u becomes u prime over u. So in this case, natural log of y becomes 1 over y. But because there's y's variable, we have to attach dy dx. And on the right side, we see that these are two distinct terms that are being multiplied together. So we have to go through product rule, f prime g plus f g prime. And then once we have our derivative, we could just try to isolate the dy dx by multiplying both sides by y. And once we have y to the right side, we basically have our derivative, but we want to represent y in terms of x, so we bring back the original equation, make that final substitution, and now we have something that is still a function where we can represent the derivative purely in terms of one variable. All right, a couple of final items here. Include units with your answer if the problem is asking for it. Okay, but it's not wrong if you always want to include units. That's fine as well. No need to simplify answers. For instance, point-slope form is just as good as slope-intercept form. And that also goes with problems as well. On the free response portion, there's no need to simplify answers. So if you have a messy answer and numerically it's the same as a simplified form, then leave it in that form, and you'll get full credit assuming the work is right. Notation: dy dx means f prime. d2y over dx2 means f double prime. On your calculator, make sure that you're in radian mode and not in degree mode. And then I just have steps here in case you're stuck and your calculator is acting up, we can always clear the memory by following these steps on the 83 and 84, and that will get you back to your normal screen.